The objective of this video is to learn how to use the regression model that we were building in previous videos for predictive purposes. What happened to the validation set? Did I happen to forget about it? You may ask. Good question. But the truth of the matter is I did not forget about it, and it has been waiting to be used for the evaluation of predictive accuracy of our model. How to do this? Here is how. Let us remember that here we have 5 patent documents intentionally kept separate in the validation set. Now for each we'll predict the examination time just as we estimated the examination time for that patent document, the one that had 28 claims, remember? In other words, take each document from the validation set, plug its corresponding number of claims in the estimated regression equation, and get the prediction. Now, let us not forget that for each patent document, we in fact know how long it took them to get granted. Thus, for each of our predictions, we can find the amount of error that we make by simply calculating the residuals. Now, having these 5 residuals, how can we come up with one number that describes the magnitude of offshoot made by us? There are a number of such measures, and here I will explain one that is among the most intuitively appealing in my view. The mean absolute percentage error, or simply the MAPE, shows in percentage terms the average error that you make relative to the true values in your validation set. For each prediction, you find the residual. Just like we did, you divide the residual over the true examination time, take the absolute value of the result, then you average those relative errors, and finally multiply the result by 100 so that you can represent the number as a percentage. In our case, the MAPE of 33.6% indicates that when predicting the examination times for the 5 documents in your validation set, on average, you were roughly 33.6% off relative to the true examination times for those 5 documents. Whether that is good or bad really depends on the predictive accuracy of alternative models that you would want to try. Those alternative models may include variations of the model that we entertained here, or regression approaches that are different in nature. Notice that the model that was entertained can be further refined, for instance, by considering transformations of independent variables, tentative addition of new independent variables that may be somehow associated with the examination time, or modeling the variability of data in addition to modeling the average examination time, and a number of other approaches. There are numerous ways in which the given model can be refined with the hope of producing a better fit and hopefully also more accurate predictions for the data in the validation set. In addition, there are a number of other statistical modeling approaches that one may entertain on this data. For instance, the decision tree approaches such as regression trees, or nearest neighbor approaches such as the k-nearest neighbor method for regression, and other more sophisticated yet worthwhile approaches. Also notice that one can very easily obtain prediction intervals for the predicted values, and in fact, modern statistical software often provide these intervals upon request. Let's also not forget that the random breakdown of training and validation sets was only one of many possible such breakdowns. As was very briefly indicated earlier this week, a more comprehensive approach exists where instead of just taking one random breakdown of training and validation sets, many such breakdowns are taken, and for each the predictive accuracy of the resulting model is calculated, and at the end those predictive accuracies are somehow combined, for example by averaging, and this provides a more reliable estimate of the predictive accuracy compared to when just one breakdown of training and validation set is chosen. This is the so-called k-fold cross-validation that I indicated earlier. Also notice that whatever the relationship emerging from a careful application of the regression method is, it only establishes an association between the set of independent variables and a dependent variable. It It simply is an association and should not be confused with causality. Thus, in the context in which the regression was just described, to say that there exists a causal relationship between the independent and dependent variables is incorrect and should be avoided. In summary, through the developed simple linear regression, we scratched the surface of a pretty complex predictive problem, and really there are a number of ways to take this method further on this example. I hope that you appreciated the intuition and the usefulness of linear regression. I do hope that you found it interesting enough to pursue further.